yes, so the title of my presentation is Using RISE for Solving Nonlinear Regime Switching DSGE Models. I'd like to introduce by asking a question, why regime switching? Well, the steady state is not steady. We keep writing models with constant parameters, and we keep chopping our data sets, hoping that, the world will stabilize. This is not the case. We've seen that past events may reoccur. We have disasters, we have high inflation, we have financial crisis, just to mention a few. I've been amazed by the way people typically address the question of the zero lower bound. And my sense is that it is a regime switching problem, in part because when the central bank reaches the zero lower bound, it starts doing something else. It can no longer use the interest rate as a policy instrument, so it resorts to unconventional policies and so on. And so the only way to capture that, because the data in that environment are clearly a function of what the central bank is doing. And so forgetting what the central bank is doing and just focusing on ensuring that the interest rate doesn't go below zero, I think it's a bit incomplete. So I tend to see the zero lower bound as a regime switching problem. There are changes in behavior in all kinds of ways, and this is just one example. Sometimes it's easy to keep a commitment, to keep a promise. Some other times, perhaps because the shocks are large, you can just, central banks would just start doing discretion. In an environment where things change like that, agents form expectations over alternative future regimes. And so the things like precautionary behavior become important. So an adequate handling of such nonlinearities definitely, unfortunately, requires regime switching. Okay, how can RISE help? Well, RISE stands for Rationality in Switching Environment. It's a MATLAB toolbox primarily designed for solving, estimating, and analyzing macroeconomic models subject to regime switches. RISE tackles massively difficult problems in a seamless fashion. It's flexible and very easy to use. In a nutshell, what RISE does is solves fifth-order perturbation of regime switching DSGE models. It does DSGE VAR, VARs and structural VARs with and without regime switching, panel VARs with and without regime switching, proxy VARs with and without regime switching. It does optimal policy under commitment with and without regime switching, optimal policy under discretion with and without regime switching, loose commitment. And that is the situation in which from time to time policies under commitment and some other times policies under discretion. Of course, we have forecasting and conditional forecasting, both in linear and nonlinear models, deterministic and stochastic simulations, three forms of derivatives, symbolic, numerical, and algorithmic derivatives. In terms of estimation, maximum likelihood, Bayesian estimation, indirect inference, time series and reporting, derivative-free optimization, global sensitivity analysis and uncertainty quantification in the form of high-dimensional model representation and Monte Carlo filtering, among others. So, well, with that background, let me give you an outline of the rest of the journey I'd like to take you on. First of all, I'm just going to list a few studies that have been successfully conducted using the RISE toolbox. Then I don't take it for granted that everybody knows what a regime switching DSGE model is. So I'm going to talk a little bit about that. And then I'm going to have two applications, two examples so to speak. I'm still working on them. The first one is just going to be an illustrative example, and I'm just going to show the RISE implementation, and then I'm going to talk about a more substantive application. So that's kind of where we're going. Okay. So then there are lots of studies that have been done with RISE. I'm just going to mention a few in passing. Challenges for macro models used at central banks by Linde, Smets, and Wouters. Do central banks respond to exchange rate movements? A Markov switching structural investigation. Yeah, is monetary policy always effective in complete pass-through in a DSGE model? Other studies have to do with the zero lower bound, the forecast uncertainty in the neighborhood of the effective lower bound, how much asymmetry we can expect, oil and macroeconomic instability. This is a paper that I co-authored with Björn Land and Larsen. And that paper is very interesting in the sense that it kinds of disentangles the source of macroeconomic instability rather than having all the instability lumped in one block. We separate the instability that may come from oil shocks from the instability that may come from other shocks. One key result that we find in that study is that policy tends to be effective when shocks are small. When shocks are large, then the effectiveness of policy declines. So I think it was a very interesting result. We also find that the key explanation for the great moderation is not what some people have thought to be the good policy. Of course, policy was trying to do its best, but ultimately it's the fact that shocks quieted down that we had the great moderation. In Chang, Maih, and Tan, 2021, we investigate the origins of monetary policy shifts. We present a new approach for regime switching DSGE models. We have a paper on leaning against the wind, or several papers, I think. Some other people have used RISE to study the problem of leaning against the wind. I'm just listing some papers like this just to give you an overview of what can be done, what people have used RISE for. Okay, for instance, in Maih, Mazelis, and Moto, the 2021 paper, we studied the asymmetric policy rules in the Euro area and the US. Yes, so it's a framework that is very interesting for studying asymmetries. So I'm not going to bore you with the details of each paper. I just wanted to give you an overview of some of the things that have been done. Okay, now let's talk about the regime switching DSGE model. The regime switching DSGE model is this system, the top equation that you see there. PRRT plus 1 is the probability of going from a regime RT today to a regime RT plus 1 tomorrow, and that probability is potentially a function of the information that we have up to time t. Okay, F, it's kind of the DSGE model as we are used to. XT is the vector of all endogenous variables, but as you can see here, there is a behavior when we are in regime RT, and that behavior need not be the same when we are in regime RT plus 1. XT minus 1 is the path that's given. Theta is the vector of parameters, and it is indexed with RT, as you can see. That means that those parameters are potentially switching. Epsilon T is the vector of stochastic shocks. ET, capital ET, is the expectations operator. okay? The number of regimes here is finite, it is H. So today we are in regime RT, and RT plus 1 varies from 1 to H. So this is the regime switching DSGE model. Of course, if H is equal to 1, we have the constant parameter DSGE model. So everything that we do with a constant parameter DSGE model, we can do with a regime switching DSGE model. Okay? So when we solve these models, what we get regime-specific policy functions as the equation, the top equation there says. But then if that's the solution or a solution of the model, then of course it ought to be the case that if we insert that solution into the generic problem and we take the expectations, we should get 0, okay? But then as you can see, and as it was already clear from the previous slide, when we are in some regime RT today, we worry about what potentially will happen in future regimes. So agents form expectations, right, as you can see here, about all possible future regimes. And this is very, very interesting. I always take that a small example to illustrate this. That is that if you are driving a car and then you are told that no matter what you do, nothing bad can happen, of course, maybe you'll start driving recklessly and so on, because nothing bad can happen, right? But that's not how people drive in real life. In real life, people drive carefully. And why is that so? Well, could it be the case that there exists a regime, okay, let's say the accident regime, that we do not want to visit, and it is because we form expectations over such a regime that in normal times we drive carefully, which means that, you know, what we expect about the future influences our behavior today. And this is a key property of this type of solutions. Okay. And by the way, this is not what the assumption that we have or the type of results that we find in constant parameter DSGE models, because in that environment, we just assume that no matter how large the shock is, eventually we will return to the steady state. And as I said earlier, how steady is the steady state? Okay. So how do we solve those models? Essentially, there are 3 broad classes of numerical methods for addressing this type of environments. One can use projection methods. Projection methods will rely on a choice of pre-specified grid of points. They tend to be accurate and fast when the number of state variables is small, and computationally prohibitively expensive when the number of state variables increases. We can solve these type of models using stochastic simulation. Stochastic simulations are going to rely on simulated series. They're easy to compute, but numerically unstable and have poor accuracy. My preferred type of solution methods remains perturbation. Perturbations are going to rely on some approximation points, and they are useful for handling large-scale systems, but the accuracy can be poor the further we are from the approximation point. That's a criticism that people who use other techniques tend to level against perturbations. But in my experience, perturbation methods work well. Okay, so the problem is that we do not know how to find the T function, the solution, okay? And all those techniques that I've told you about are going to approximate the true solution. And this is a p-order perturbation of approximation of the true solution. RISE implements in the environment of regime switching DSGE models 2 types of perturbation: Foerster, Rubio, Ramirez, Wagoner, ENZA 2016, Maih and Wagoner 2018. So the state variables are then going to be xt minus 1, that is the lagged endogenous variables, the perturbation parameters, sigma, because we are doing perturbation, and the vector of shocks. But then, of course, we can also expand that vector of shocks using, if we have anticipated shocks. And this is what, yeah, we did many years ago. Okay, so let's look at a very small example just to show you how simple RISE is to use. I use this three equation system by Foerster, Rubio, Ramirez, Wagoner, and Za. The first equation is an Euler equation. The second equation is a nonlinear Phillips curve. The third equation is a monetary policy reaction function. There are two parameters that switch in this economy. The first one is the growth rate of the economy, mu, okay? And then the second one is the reaction to inflation. And so then those parameters can assume values 0.03 and 0.01 for mu, and 3.1 and 0.9 for psi. So if you look at the values of psi, you clearly see that in the second regime, the Taylor principle is not satisfied, okay? But in a regime switching model like this one, this is not a problem. The system can still be stable and determinate even if we have such a situation. All depends on the values of the other parameters as well as including the transition probabilities, which here are constant. So the probability of staying in regime 1 is equal to the probability of staying in regime 2 here, and it is 0.9. If we have a system like this, how do we implement it in RISE? That's very easy. We declare the endogenous variables using the keywords at endogenous. Pi, y, and r are the endogenous variables of this system. We declare the exogenous variables. There's only one in this particular case. That's the monetary policy shock. And we declare the parameters that are constant, okay? And we also have some transition probabilities. Here, the first thing to do is to give a name to the Markov process controlling the switching parameters. Here, I've called it Dan. And Dan here has two states. Okay, this is what this says. And Dan controls the behavior of mu and psi, which means that mu and psi move in locksteps. Okay, Dan gives rise to transition probabilities from going from state 1 today to state 2 tomorrow, and from state 2 today to state 1 tomorrow. And then we have the model equations at model, and then we declare the equations. Okay. So if you are able to write a file like this, then you can give yourself a pat on the back. You understand a lot already about the workings of RISE. Everything else is optional. It can be put either inside the model file or outside, like here, the system solving the steady state, as well as the parameterization of the model. But this can be put outside the model file. Okay, I don't know how I'm doing in terms of time. Perhaps I don't know. I'm not keeping the time. I don't know when I started.
You're doing very well, Junior.
Okay. So in terms of an application, the simple application, this is something that I started on not long ago. I thought about introducing, presenting something about rare disasters in a regime switching DSGE model. So I just have a small Nukenjan model, which features a representative household, a representative finished goods firms, a continuum of intermediate goods firms, a central bank, capital and technology subject to rare disasters. So just a simple framework. Then I'm not going to show you the rest of the model. I'm just going to show you the key equations here. we have a non-stationary technology shock, and the mean of that shock is affected by the rare disaster process, DT here, okay? That process is as is described by equation 5.3 here, and tau, this, it's not tau, it's zeta, the parameter here is regime switching, okay? So what is going to happen, we're going to see it on the next slide, is that this parameter can take on two values depending on what the regime is. And we have a shock process here. That is, if it hits and then it catches us in a situation where this parameter is positive, then that generates a big shock to DT that translates, that affects the growth rate of the economy, and that destroys also capital, as you can see here. Okay, so that's kind of the disaster mechanism that we have in this model. Okay, as Doug was saying earlier, there are tons of applications, but this is just a small example that I chose. In terms of zeta, as I was saying earlier, it can assume value 1 with a small probability p, or 0 with a large probability in each period. Okay. However, if we ever draw the wrong state, it's going to be state 2 here. If we ever draw the wrong state, then it's going to trigger very large nonlinearities. Okay, you can think of things like climate change. You can think of the pandemics and so on. So these questions are very important, and have people have been interested in them for a long time. The problem is that how do we solve those models? People find it difficult to solve those models using perturbation and constant parameters, but that's the framework that is mostly used. And so people have to resort to tricks like transforming the disaster process, okay? So in the literature, what we know is that even third-order perturbations may generate solutions that suffer from accuracy problems. And there is a paper in 2017 that stationarizes the model in such a way that only features of the small probability of a disaster appear instead of the large original event itself that may be generated by the shock. And so in that case, only small innovations to the small probability of disaster can be accurately simulated with conventional higher order perturbation, regardless of the disaster regime. Okay, so basically you hide the effect of the big shock, and then you focus on the small probability. And so those are the type of tricks that people have used in the literature. It turns out that if we're doing regime switching, we don't need to do that. So in RISE, we are able to solve a model like that without even stationarizing it to begin with. We can do higher orders of perturbation if we want. The model that I'm talking about, I solved it for upwards of 20 state variables to up to 4th order of perturbation without any difficulties, and even with skewed shocks. Okay, because we're doing regime switching, and as I was telling you earlier, you are in normal times, you are driving your car, and you have some precautionary behavior motive, because you form expectations about what potentially could happen in the future. And so in this environment, even a first order approximation is already non-certainty equivalent. Something that we do not have in constant parameter models. So what can we do? We can, with a model like this, we can, of course, compute impulse responses, we can simulate data, we can estimate parameters. So everything that we like doing with constant parameter models. Okay, so these are some impulse responses that are not, I'm not true yet. I'm still working on refining the calibration and so on. But this is just to show you that we can compute impulse responses in such a model. This is a disaster shock. The blue line is the normal regime. And so that is going to be the situation in which zeta is equal to 0. Okay. And if zeta is equal to 0, irrespective of what happens with tau, okay, it doesn't affect d, and so we still fine. But then when the shock, if we are in a situation where zeta is different from 0, then the shock hits, it destroys output, it destroys capital, it destroys investments, and so on. Okay, and then the central bank tries to do its best to, you know, to how to say, to try to recoup or to, you know, to lower the interest rate in order to help the economy rebound. And so these are just some small impulse responses for illustrations here. We have impulse responses to monetary policy shocks. Yeah, so output falls as usual, capital falls, is destroyed, investment falls, wages fall, the interest rate here increases. That's the interest rate shock. We have the preference shock here. We have the stationary technology shock. In normal times, technology will improve, so output will increase, capital will increase, and so on. Wages are going to increase, investment increase, but in the other regime, output will fall. Okay, we have the permanent technology shock as well. And yeah, so these are just some small impulse responses to illustrate what we can do with such a framework. Of course, if people are interested, you know, they can analyze what policy should do in such an environment. They can, one can evaluate the performance of alternative policies, etc. Be it fiscal policy or monetary policy. And I think that's all I have for you today. Thank you for your attention.